All right, I'm Jes. You've seen me before. There is sort of a theme to what I do, is that computers and the real world kind of don't quite work together. There's friction there, and that friction is interesting to me. Digital stuff has killed everything. We had all this technology before. It's all gone. It's been replaced with this new generation. Is that good? So I was starting to think about that. I was thinking about what was high tech before. And the highest high tech was the Astrolabe. For 1,000 years, it was like state of the art. The medieval smartphone is like someone else's talk. It's a lot like the slide rule. It's really a combination of two ancient technologies. The dioptra is a way to measure altitudes. It's kind of like a sextant. And the planisphere, we still use them. They're star maps. And it could do hundreds of other things. It was invented in ancient Greece, or the math was. They were actually made probably in Egypt, helped touch off the Islamic Golden Age. The knowledge was transmitted back to Europe in time for the Age of Exploration and was still state-of-the-art for hundreds of years until clocks and telescopes sort of killed them in the 1600s. That knowledge has not been lost, but it is sort of rotting. There are websites, most of them are not great. The books are out of print. This guy, James Morrison, spent the 1980s and 1990s figuring out how to do astrolabe stuff with computers of that era. He wrote a textbook about it, and then he died and the book went out of print. An astrolabe is made of parts. Each part is like a standalone thing, and I was like, oh, that actually makes it approachable. I could make them one at a time and see how far I get. The heart of it is this sort of glorified spherical graph paper, which represents your local sky. So the dot in the middle here, is straight up, and the axis here is like the axis of the Earth. So the stars are turning around you. And you need a different one for where you are on Earth, how far north or south you are. Around that, when I started thinking about this, I had this PCB ruler from Adafruit. Probably some people here make PCB art. I know that's true. You can make other things with it, with that technology. And it's high precision. And I was like, I want to learn how to do that. So to make PCB stuff, you need to use a program like KiCad. KiCad is hellaciously complicated. And it has an API that I could never get to work. So I couldn't figure out how to do anything programmatically in it. But I discovered that the save file formats are plain text. And you can just edit them. So you can be like, I want to draw a line segment from here to here. I want to write a number here. I want to cut a circle, an arc. It's just numbers, right? So I wrote some Ruby code. I spent a lot of time on Wikipedia learning spherical trigonometry, which was kind of a pain, but everything I do for fun requires trigonometry, so I was like halfway there. So it's not that much code to sort of walk around the circles and project it with spherical trigonometry, and then save it, upload it to someone who can print it, and then you have a physical object that's like really beautiful. And once I had that, I was like, oh crap, I have to do the rest of this project. So the next part, actually, one more thing. So it's code, so you can make variations. So here's for the different bang bang locations, just slightly different view of the sky. Okay, so the next part. So for most of history, transparency was difficult. So to make things that approximated a transparent medium, they would just like cut big holes and stuff. These are star maps. It's not very well suited for PCBs because printed circuit boards are mostly solid. Like you can't cut a lot of holes and it still come out of the machine correctly. So I didn't know what to do. And the other thing is you can't just reuse an old design because the stars drift slightly, about 1 degree every 72 years. So these are from different centuries. And you can tell this star here is Antares, which is a bright red star, usually near the horizon. It's this point, this dragon's tongue, and this point. And they've sort of artistically designed the thing around its different positions, and you can sort of see that over the course of 800 years it's moved. And these three stars, that's like, this one's in the Big Dipper, this is the same three here, and they're like a very different configuration 800 years later. Okay, so I was like, how am I gonna do this? And I didn't know. So I just sat around thinking about it for like 3 years. And I was like, okay, no way, I can do this. I can get the coordinates. I found this Python library that can give you coordinates of stars. So I wrote this thing, just give me the where does the star look like it is from our point of view. and then more trigonometry, just sort of like lay it out. And it's like, okay, now I have this computer-generated stuff that has the points in the right places, but the art stuff is still hard. And I was like doodling, trying to figure out what am I gonna do? How am I gonna make this? And it's like a creative project, which is way harder than just pure math. And eventually what I came up with is just write thousands of lines of hand-tuned drawing commands. This took like 2 months. If you've ever done turtle graphics or logo, it's like you move in the little arrow around, turn left, turn right, go this far. I just kept doing that until I had drawn the damn thing. And then it's like, okay, now I have this image, what do you do? And I was like, well, you can cut intricate things if you have a laser cutter. So I found this company, Send Cut Send, which is great for cutting things out, but they can't do engraving. So you get the shape, but there's no text on it. I eventually found that someone else has a more expensive process called Pinocchio, where they can take the SVG and cut and engrave in one step. And then they sent me these. I was like, okay. And then I just sort of ran with that technology. To make the body of the thing, I just made several. This is me printing out PDFs of the different layers and like holding up to light, say, do these still line up? And they do, and I just screw them together, and I have a thing. And then the back, I don't have time to get into it, but this is sort of a standard like Western style astrolabe where all the different apps for doing trigonometry and doing calendar and stuff are all on this side. The Arabic versions had much more variation. Okay, now there's just the only things left are the pointers. I did that in like actual 3D printing. This is OpenSCAD. Its language is like, I want to put a cube here, and then I want to cut a hole in it. And so you're doing a lot of geometry stuff, and it's unions and differences and addition and subtraction. So it's not that bad, and you can watch, you can have the thing on the screen and just sort of move around until it looks right. And then you just send it to Shapeways, except they went out of business, so you can't do that. But there's this other service called Craft Cloud, and they can do metal. The way it works is they 3D print wax, and then they pour molten metals into the wax, so you can do lost wax casting, but it's all done by computer. And the only downside is you have to get it done overseas, but I went with the cheap ones, and it was fine. And you put it all together, and it looks like it's a real thing. And so like to show that this is actually still useful, I'm gonna do a real quick demo. It's a simulation. You need direct sunlight to tell the time, and I'm in the shadow right here. But we're gonna do it. So first off, you need to measure how high the sun is. It's about 60 degrees up in the air right now. And if you wanna line up the two holes in the alidade is the Latin word for it. So the sun comes in the one hole and casts light on the smaller hole. Because if you're measuring like a regular star, you would look through it, but don't do that with the sun and hurt your eyes. Okay, so it's about 60 degrees. You can see the shadows. They're casting about a 60-degree triangle. And then you also need to know where the sun is on the zodiac, on the ecliptic. And so you have a calendar scale. It's August 24th. That's about 2 degrees in Virgo. You find that, you flip it over. Hang on, I should be holding my thing up. You flip it over, you look on this side, and it's like, okay, 2 degrees Virgo. These ticks are actually every other degree because it's tiny. So that's about here. And then you line that up. So, okay, so 2 degrees Virgo is at the 60-degree line, right there. And then you just put the clock hand, it's called a rule, from there to the outer scale, which has the times on a clock, 10, 10:30, 10:45, a little more, 10:55. Okay, but that's sundial time, that's ancient time. So you need to convert modern offsets. So it's about 1 hour off for daylight savings time. We're about 2 degrees west of the time zone's meridian, so you add 8 minutes for that. And then because it's August and we have modern timekeeping has this analemma thing, you have to add 2 more minutes, and it was about 2:05 when it was perfectly 60, 12:05, it was perfectly 60. And so I'm about out of time. But thank you all so much.